Okay, here's another method to compute determinants. We've already seen expansion by minors. This is one we can also use row reduction, it turns out. But in that case, we need to understand how each row reduction step affects the determinant. And so, yeah, the effect of row reduction on the determinant. So remember, there's three different possible row reduction steps, right? So the first thing we can do is we can scale a row, by a scalar, let's say by k. And let's think about what that does to the determinant. Well, we've sort of seen already from these area of properties that if we scale one of the vectors, if we think of the determinant as the area or the volume formed by the column vectors and the row vectors, and if we scale one of those rows or columns, then we actually just make the box, the parallelepiped, bigger by that factor, right? So if you scale a row by k, it's sort of like taking the volume of let's just say we scale the first row. Let's just say we have n rows and we scale the first row by k. We've already seen that just scales the volume by the same factor. You're just scaling one dimension of the box, right? And so that implies that the determinant gets scaled. So say we have our matrix A. So say scale a row of the matrix A. Determinant gets scaled by a factor of k. We multiply the determinant by k. Okay, so that's the first effect. So if we scale a row, we just multiply by the same factor. The second row reduction is to swap two rows. Right? But if we do that, we've seen that if we swap two rows in a volume, remember it's a signed volume, it has a plus or minus sign associated to it. So if we do something like, let's just say I swap row 1 and row 3 of, say, let's just pretend like it's like a 4x4 matrix or something, and that's negative the volume that we would get from the original R1, R2, R3, R4. Right, I'm just saying, if we swap these two, for example, just easier to use an example than to try to write that in general. Well, that implies the determinant switches sign. So if it's positive, it becomes negative, and so on. Right, okay, so that's the second effect. The third one, the third row operation, seems like the most complicated. So we add a multiple of one row to another. Right, we know this. Now this is kind of a fascinating argument. Let me just give you say a 3x3 example. So if we have, let's just say we have the volume, let's say we take some 3x3 matrix. So let me just write this as again, this is row 1, row 2, I'm giving them as vectors, and row 3. So the matrix whose rows are R1, R2, R3. And let's just say we add 5 times row 2 to row 1. Okay, then what we're looking at is the volume this is an example, the volume of R1 plus 5 R2, R2, R3. Right, the volume formed by those. But we've seen that these break up over the plus sign, right? That plus sign right there, we can actually break the volume up over that. That's one of our big properties. So that is the volume of R1, R2, R3, the volume formed by those, plus the volume formed by 5R2, R2, and R3. And let's just focus on this second term for a moment. This, we've scaled a row, so that's 5 times the volume formed by R2, R2, and R3. Make sure that's really clear that these are the same subscript, R2, R2. And what we've noticed is, what we said with these volume properties is that if two of the vectors are the same, then you don't really form a volume at all, right? You just get a volume of 0. So in fact, this right here has volume 0. And so what that means is that these two things are equal. In fact, this just equals that. We don't even have to worry about this part. And that's kind of amazing because it means that the volume's not changed, which means the determinant is not changed. So in this case, the determinant of A is unchanged. And so that's kind of awesome. So that means that row reduction steps, if we apply row reduction steps to a matrix, we can track the changes in the determinant, and the determinant doesn't really change that much because probably the step we use the most is the add multiple of one row to another. So that doesn't change the determinant. And then switching 2 rows or scaling a row switching 2 rows just scales the determinant by -1. Scaling a row by 5 scales the determinant by 5. So if we just track those scalings, then we can sort of compute the determinant this way. So let me give you an example. Probably the best thing to do. And this is actually the matrix we used in the expansion by minors example. So let's just say A is, we write this out. It's the matrix with rows -1, 3, 1, 4. Second row is 0, -1, 0, 5. Third row is 2, 1, 1, 2. And the last row is -1, 3, 0, 1. -1, sorry, the last two is a -1. Okay. And so let's just think about doing row reduction operations on this. I'm just going to actually write out the row reduction. And I just want to get to echelon form. I don't even have to go all the way to reduced echelon form, because once it's in echelon form, the matrix is upper triangular. And we've seen that the determinant of an upper triangular matrix is just the product of the diagonal elements. So I'll say that again when we get closer, but let me just write this out. So I'm not even going to worry about scaling the pivots to be 1 either. I can just leave them, like I'll just leave this top left pivot, I sort of focus on this top left pivot first. Just leave it as -1, but I want to clear out, these entries and make them 0. So what would we do? Well, we would take, one of the things we would do is take row 3 and actually add twice row 1 to it, because that will cancel out the 2. And we can take row 4 and subtract row 1, right? Because the -1 will cancel, and that'll make zeros there. So if we do this, okay, first 2 rows are the same. Just go through these steps. I like to do everything I write explicitly in these videos, but you can always sort of fast forward through or do it on your own and then check. So I'm adding twice row 3, right? So this becomes 7, 3, and 10. And the 4th row, we get a 0 there. We get a 0 there, which is sort of nice. We get a -1 and a -5. Okay, And we'll do that. We'll track the determinant changes in a minute. Let me just do the row reduction steps. So similarly, I can, okay, not too much is going on. Notice the determinant's not changed at this point. Now we can focus on this pivot and clear out, well, the 0 is already cleared out, but we can clear out that 7. So we're going to take row 3 and we're going to subtract, nope, we're going to add 7 times row 2. Right, okay, so we get, the only row that's changed is row 3. So we get 0, 0 there. This is still 3. This becomes kind of big. This is 45. 0, 0, minus 1, minus 5. Okay. And now just to illustrate, I mean, we could even, we can do a couple things here, but I want to illustrate all 3 of the row reduction operations. So let's actually swap row 3 and row 4. Let's write that out real fast. Hopefully I haven't miscopied anything. So now this is row 3, and that's row 4. And notice, I mean, if you're doing this, you would really just now, add, 3 times row 3 to row 4. Again, I want to illustrate the different row reduction steps, or the different things you can do. So let's just actually take row 4 and scale it down by 3. I noticed that 45 is a multiple of 3 also. Not necessary. I just want to illustrate how it's going to change the determinant. So this becomes a 1, and that becomes a 15. And then as our last step, right, we can add row 3 to row 4. So take row 4 and replace it by row 4 plus row 3. And if we do that, okay. So now we're going to be in echelon form. It's a nice staircase pattern. 0, 0. So we add these, we get a 0 there, and we get a 10 there. Okay, and now I want to track, and so from here, the determinant to this last matrix is easy. You just multiply the diagonal elements. So let me give these matrices all names. So let's call this matrix at the top here M1. I'm just going to give, because we started with A, right? Let's call that M1. Let's call this matrix M2. Let's call this matrix M3, M4, and M5. And here's what we say. Well, we've already, okay, so the determinant of A, I'm just going to do this here so I can keep all the matrices on the same screen. The determinant of A, well, when we go to determinant of M1, it's unchanged, right? We've just added multiples of one row to another. Actually, same thing for M2. Oops. The determinant of M2. So nothing's changed at that point. The determinant of M3 is negative the determinant of M2 because we swapped rows going from M2 to M3. And so that's negative the determinant of A. And the determinant of M4 is 1/3 the determinant of M3 because we multiplied by 1/3. I keep writing determinant. So that's negative 1/3 the determinant of A if we just keep tracking this. Right? Just plug it in. And then, right, because the determinant of M3 was negative determinant of A. And then the determinant of M5, again, that's just an atom, one multiple one row to another. That equals a determinant of M4. So that's still negative 1/3 the determinant of A. And so what we can see then, if we sort of put this together, well, I've been tracking the changes the whole time. That means the determinant of A is -3 times the determinant of M5. But the determinant of M5 is just the product along the diagonal because it's upper triangular at this point. And so that is equal to -3 times -1 times -1 times -1 times 10. And -1s on all those diagonal elements. And so 4 minus signs makes a plus, so then we get 30. So that's our determinant. This is how you can track. And in fact, this is the same example using expansion by minors video, and that also had determinant 30, so it checks out. So that's the idea. You just sort of, you can be a little more, you can do this a little more systematically if you do it a few times, where you just sort of track each time how the determinant's changing and then make sure that you're, you'd have to be a little careful because, for example, we scaled down, wrote down by a third, but because we were going from the determinant of A to the determinant of M5, then really going backwards, we scale up by 3. So that's why we got a 3 times. So there's ways to be systematic about it, but that's the idea. All right.